Thank you for your introduction. Hi everyone, I'm Jiawen. Today I'm glad to present our paper Secure Transformer Inference Made Non-Interactive. This is joint work with Xinpeng, Lipeng, Kejia, Wenjie, Yinhao, Xiaoyang, Jianliu, Kuiren, and Xiaohu Yang. So let's get started. Transformer have revolutionized artificial intelligence. They excel in a wide range of applications such as language translation, content generation, and question answering. However, these applications often involve the user-sensitive data, leading to growing concerns about user privacy. For example, OpenAI has developed ChatGPT as an online interface inference service, along with a public API for developers to access the platform by submitting prompts and messages. While this approach is convenient, it poses significant risks to data privacy, as the content submitted by the users may contain private information. And secure inference is a two-party cryptographic protocol, enabling model inference to proceed in a private manner, where the server learns nothing about the input submitted by the user, and the user learns nothing about the server's model, except for the inference result. Many such protocols were developed for convolutional neural networks in the past few years. For non-interactive secure inference, there are two key differences between transformers and the CNN model. Firstly, large-scale matrix and matrix multiplication. Previous work such as Cheetah and Iron compute matrix multiplications via inner dot products and employ sparse packing for the results. As a result, the majority of data slots in the ciphertext are often wasted, which introduces additional communication overhead. However, in transformer inference, the input dimension of matrix are often much higher, leading to increased computational cost. Consequently, it's useful to develop a new matrix multiplication protocol that is both time and space efficient. Secondly, higher dimension inputs to Argmax. The last layer of both CNN and transformer is Argmax, whose input is a probability vector, with each entry being the probability of an output label candidate, where m labels in total. The inference output is a label with the highest probability. Currently, the state-of-the-art FHA algorithm for Argmax was presented by Phoenix in CCS 22. Which demonstrate a computational complexity of OM. In CNN classification tasks, M is usually not very large. For example, M is 1,000 in ImageNet 1K. However, in transformer-based NLP tasks, M is the vocabulary size, which is about over 30K in BERT and over 100K in Llama 3 8 billion. It's noteworthy that most of previous works are interactive based on multi-party computation, which has two significant disadvantages. First, MPC will bring substantial communication overhead. Second, it's difficult to be compatible with hardware acceleration via GPU and FPGA. Because the bottleneck of MPC-based protocols is the communication overhead. For example, BOLT take about 59 gigabytes of bandwidth consumption, over 10K interaction runs, and more than $5 for a single word inference. This is not very practical in real-world inference. In our work, we propose NEXUS, the first non-interactive protocol for secure inference, for secure transformer inference, based on fully homomorphic encryption. We achieve efficient and communication-optimized matrix multiplications, and efficient Argmax and the other nonlinear function evaluation, and and we provide an implementation of NEXUS on both CPU and GPU. Here's a toy example for matrix multiplication in fully homomorphic encryption. In this way, we did not waste any slots, but we need one party to send 6 SMD ciphertexts filled with the same elements, which will bring huge communication overhead. Here is our solution. The server compresses its elements into polynomial by coefficients, encrypt it with public key, and send it to the client. Then in the client side, he can expand the ciphertext into 4 ciphertexts, where each element stays in the constant term position in the ciphertext. We have proved in our paper that the encryption of a polynomial with only constant term is exactly an SMD form of n identical values. Note that in transformers, this SMD-packed ciphertext can be reused because the model parameters remain unchanged during secure inference, and only the content of the input matrix changes. The expand algorithm was first proposed in COPR, which only needs log n levels and is easy to be computed in parallel. Here is the amortized cost of matrix multiplications. We include an example using BERT-based parameters and different number input queries. The result shows that we have lower amortized computation and communication cost. Then for the efficient Argmax evaluation, let's start with some preliminaries. To defend against membership inference attack, a common approach is to output the probability of the most likely K classes. The smaller the K is, the less information the model leaks. In the most extreme case, the model returns only one label of the most likely classes. That's Argmax. For example, the Argmax of 2341 is 0010 because 4 is the maximum value. The sign operation is calculated with higher degree composite polynomials in ciphertext, and the max operation can be simply converted from the sign operation. In previous work, Phoenix adopts the idea of bubble sorting to compare each element with its nearby elements by rotating the ciphertext and calculated the difference. After calculating the sign of the difference, we can use it as a scoreboard. If an element is larger than the elements on the right, add 1 point. If it's smaller, subtract 1 point, so that the largest elements will definitely have the highest score. For n-dimension input, it needs n times rotate and sign operations. In our method, in the right side, we notice that you can easily compute the Argmax if you have the max value. And we propose the quick max algorithm with only log n time rotation and sign operations. This form is like computing the roots of a binary tree in log n times. And f function can be any associative function, such as sum, max, min function. And for other nonlinear functions, we follow similar methods presented in previous works. For JLU, we approximate using a piecewise polynomial like Bumblebee and Puma. For linear norm, we use the Newton's iteration to calculate the inverse square root. You can refer to our paper for more detail. Here's the performance of the nonlinear functions. NEXUS is based on CKKS, which is a leveled homomorphic encryption scheme. Once a ciphertext level becomes too low, bootstrapping is required to refresh it to a higher level to enable more multiplications. As the bootstrapping operation is expensive and the most scales and the cost scales linearly relative to the number of ciphertext inputs. Its placement is crucial for the overall performance. This picture shows the placement of bootstrapping for a BERT-based transformer employing NEXUS. The width of the building blocks represents the dimension of the input and output. Matrix multiplications will bring about a change in dimensions. We try to perform bootstrapping when the dimension is the smallest. That is, when the number of packet ciphertext is at the least. We list the runtime for each individual operation in NEXUS. We batched 32 inputs in total and evaluated the benchmark on a machine with a 32-core CPU and 4 A100 GPUs. Depth represents the change in available multiplication depth before and after the operation. Runtime is the amortized latency of each input. We can see that bootstrapping is the most time-consuming part of the entire process, requiring over 500 seconds and occupying over 60% of the total time in our CPU and GPU implementation. Here is the end-to-end comparison with the existing secure inference frameworks using with BERT-based. The input to the model consists of 128 tokens. NEXUS has the lowest communication overhead and the financial cost. At the same time, since there is only one interaction throughout the process, NEXUS will be very compatible with hardware acceleration. It only takes half a minute to complete a secure inference under GPU acceleration, with only 5 cents per token. We have open sourced our code on GitHub a few months ago, and we already got 86 stars. It's worth mentioning that we have implemented CKKS bootstrapping the first time on Microsoft 4 version, and we have provided our CUDA source code for the first time to accelerate Microsoft CO. Here's a summary of our paper, and thank you very much.
Impressive work. Anybody would like to ask a question?
Okay. I have a question for you and a nice presentation. I'm curious about how to calculate the financial cost in your paper. Would you please explain it more details?
Okay. The financial cost, we refer to the Amazon Web Service pricing policy. For example, for 1 gigabyte transfer, it needs 9 cents, and for 1 hour CPU used for a 64 core CPU, it needs about $1 per hour.
Okay, thank you.
Okay, thank you.
Any other questions? Yeah. Please go ahead.
Thank you for your presentation. I'm just curious whether your matrix multiplication protocol can be extended to support non-interactive protocol for the inference for other models like graph convolutional networks with sparse matrix multiplication. Thank you.
Oh, okay, thank you. All of the transformer-based models can adopt. This architecture is the same for both Llama, Gamma, Mistral, Phi. All these transformer-based models have the same or similar architecture, and our protocol is designed for is a overall design, and it can be compatible to all transformer-based models. For you mentioned the graph model, such as CLIP and any graph some VLM, such as DeepSeek VL, it can also they also use matrix multiplication and some activation functions. So our proposed protocols also can be used in these models.
Thank you.
Just a little bit comment. The matrix multiplication here is not designed for sparsity matrix. You have to view it as a dense matrix. That's it.
Thank you. Thank you.
That's for the explanation. Yeah. Thank you.
Thank you.